Hey guys, welcome to yet another class on system of variable composition. In this class we will discuss about thermodynamics of mixing in terms of Gibbs free energy of mixing, entropy of mixing, enthalpy of mixing, and we will also solve few numerical problems. Before starting the class, I want to tell those students who are new on this channel that this is the third lecture on this unit, and I have given the link for the first and second lecture in the description box. Please watch those classes, and if anyone have any questions, you can post them in the comment box anytime you want. I will try my best to clear your doubts and solve your questions. And if you are interested to learn physical chemistry and want to clear your basics, then please subscribe this channel. Your love will encourage me to take better classes day by day. I have also included spectroscopy classes and will include quantum chemistry very soon. So without any further delay, let us start today's class. Thermodynamics of mixing. The Gibbs free energy of a mixture is dependent on its composition, and at constant temperature and pressure, a system tends to lower its Gibbs free energy. If two or more gases mix spontaneously, it must corresponds to decrease in free energy. So this is the basic of thermodynamic of mixing in terms of the Gibbs free energy change, right? So let us discuss the Gibbs free energy of mixing. So let us consider that we have two gases in two separate containers, gas 1 and gas 2. N1 is the number of moles of gas 1 and number of N2 is the number of moles of gas 2. The temperature and pressure in both the containers will remain constant, and the chemical potential mu is equal to Gm, which is the molar Gibbs free energy. So we have this relationship G is equal to G naught plus RT ln P by P naught, where G naught is the standard free energy, P is the partial pressure, and P naught is the partial pressure at 1 bar. So mu equal to mu naught plus RT ln P by P naught, give it equation number 1, where mu naught is the standard chemical potential of the pure gas at 1 bar pressure. The Gibbs free energy of the total system is therefore given by Gi equal to N1 mu1 plus N2 mu2. This implies Gi equal to N1 into mu naught plus RT ln P by P naught plus N2 whole into mu naught plus mu2 naught plus RT ln P by P naught. This implies Gi equal to N1 whole into mu naught plus mu1 naught plus RT ln P plus N2 whole into mu2 naught plus RT ln P. Give it equation number 2 because we can replace P by P naught by P. Okay. Now when the two gases are mixed, the partial pressure of the gases are P small p1 and p2, with p1 plus p2 is equal to capital P, which is the total pressure of the mixture. The total Gibbs free energy changes to Gf equal to N1 whole into mu1 naught plus RT ln P1 plus N2 whole into mu2 naught plus RT ln P2. Give it equation number 3. So therefore the Gibbs free energy change of mixing is given by del G mix is equal to Gf minus Gi, from which we can write N1 whole into mu1 naught plus RT ln P1 plus N2 whole into mu2 naught plus RT ln P2 minus N1 whole into mu1 naught plus RT ln P plus N2 whole into mu 2 naught plus RT ln P. Okay. This implies del G mix equal to N1 mu 1 naught plus N1 RT ln P1 plus N2 mu 2 naught plus N2 RT ln P2 minus N1 mu 1 naught minus N1 RT ln P minus N2 mu 2 naught minus N2 RT ln P. From this we can write N1 mu 1 naught plus N1 RT ln P1 minus N1 mu 1 naught plus N1 RT ln P plus N2 mu 2 naught plus N2 RT ln P2 minus N2 mu 2 naught minus N2 RT ln P. So cancelling this and rearranging, we can write del G mix equal to N1 RT whole into ln P1 minus ln P plus N2 RT whole into ln P2 minus ln P. This implies del G mix equal to N1 RT ln P1 by P plus N2 RT ln P2 by P. Give it equation number 4. Now we know that Ni by N equal to Xi. This implies Ni equal to N into Xi, and using the Dalton's law, Pi equal to Xi into P, which gives Pi by P equal to Xi, we get del G mix equal to N1 Nx1 RT ln X1 plus Nx2 RT ln X2. This implies del G mix equal to nRT whole into X1 ln X1 plus X2 ln X2. Give it equation number 5. Since the mole fraction X is less than 1, so the logarithm terms in equation 5 are negative, and as a result delta G mix is less than 0 or negative. Thus we can say that perfect gases mixes spontaneously in all proportions. This is because that from the thermodynamic point of view, we know that if a process is spontaneous, then the Gibbs free energy change of that system is always less than 0. So therefore we can write that from this equation number 5, that is delta G mix equal to nRT whole into X1 ln X1 plus X2 ln X2. This implies we can write del G mix equal to RT whole into N into X1 ln X1 plus N into X2 ln X2. This implies del G mix equal to RT N1 ln X1 plus N2 ln X2, from which we can write del G mix equal to RT summation of Ni ln Xi. Give these two equations, equation number 6. So the Gibbs free energy of mixing, Gibbs free energy change of mixing is given by this equation numbers 6. Okay. Now let us solve a numerical problem based on the Gibbs free energy change of mixing. The problem is a container is divided into two compartments. One contains 3 mole of hydrogen at 25 degrees centigrade and the other contains 1 mole of nitrogen at 25 degrees centigrade. The pressure of H2 is twice than that of N2. Calculate the Gibbs free energy of mixing when the partition is removed. Assume perfect behavior. So let us try to solve this problem. Let us assume that we have taken the two gases in two containers separated by a partition, where N1 is the number of mole of hydrogen, which is equal to 3, and N2 is the number of mole of nitrogen, equal to 1 mole. So the pressure of hydrogen gas is 3p and that of nitrogen gas is P. So when the two gases are mixed together, the partial pressure of Pi becomes 3p by 2 and that of hydrogen becomes P by 2. This is because when the two gases are mixed, then the partial pressure of the two gases are equal to half of their individual pressures before mixing. So here we are using equation number 4, which gives that delta G mix equal to N1 RT ln P1 by P plus N2 RT ln P2 by P. So from this relation we get del G mix equal to, replace N1 by 3, so 3 RT ln 3P by 2 divided by 3P plus 1 into RT ln P by 2 divided by P, because P2 is equal to P by 2 and P small p is equal to total pressure P. So this implies we can write del G mix equal to 3 RT ln half plus 1 RT ln half, which gives minus 3 RT ln 2 minus RT ln 2. Just inverting the logarithm term, it will become minus. So it gives del G mix equal to minus RT ln 2. Now substituting the value of RT and ln 2, we get del G mix equal to minus 4 into 8.314 into 298 into 2.303 into 0.3010, which is the value of the log of 2. So it on simplifying, it gives del G mix equal to minus 6869.84 joule per mole, and when we convert it into kilojoule, it becomes del G mix equal to minus 6.87 kilojoule per mole. So this is the value of the free energy mixing of nitrogen and hydrogen gas, and it becomes negative, which means that the nitrogen and hydrogen gases are mixes spontaneously. Okay. Now let us discuss about the entropy of mixing. We know that del G by del T at constant pressure and composition is equal to minus S, right? So from this we can write that S equal to minus del G by del T at constant P and give it equation number 7. And also we have derived that relationship that del G mix equal to nRT whole into x1 ln x1 plus x2 ln x2. So therefore we can write that del S mix equal to minus delta G mix by del T at constant P, N1 and N2. So this implies del S mix equal to minus del, replace del G mix by nRT whole into x1 ln x1 plus x2 ln x2 divided by del T. This implies del S mix equal to minus nR whole into x1 ln x1 plus x2 ln x2. Give it equation number 8, since del T by del T is equal to 1. This implies del S mix equal to minus R, replace x1 by n into x1 whole into ln x1 plus replace x2 by n into x2 into ln x2. This implies del S mix equal to minus R whole into n1 ln x1 plus n2 ln x2, from which we can write del S mix equal to minus R and summation into summation of ni ln xi. Now consider if the number of mole equal to n equal to n1 plus n2 plus n3 plus dot dot, then n by n equal to n1 by n plus n2 by n plus n3 by n plus dot dot. So from this we get 1 equal to x1 plus x2 plus x3 plus dot dot, which is equal to summation of xi. Thus for a total of 1 mole of a mixture, we can write that summation of ni equal to summation of xi. So the entropy of mixing is given by del S mix equal to minus R into summation of xi ln xi. Give it equation number 10. Or we can write del S mix equal to minus R x whole into x1 ln x1 plus x2 ln x2. So since ln x terms are less than 0, so del S mix is always greater than 0 or positive for all proportions. We know that the entropy is the measure of disorderness of a system. That means when one gas disperses into the other, the system becomes more disordered, and hence the entropy of mixing is always greater than 0. Is it clear? In the numerical problem 1, which we have solved few minutes ago, we can also calculate the value of del S mix as follows. We have del G mix equal to minus 4 RT ln 2. From this we can write del S mix equal to minus del T of minus 4 RT ln 2. From which we can write del S mix equal to minus whole into minus 4 RT ln 2, which gives del S mix equal to 4 R ln 2. Now replacing the values, we get del S mix equal to 4 into 8.314 into 0.6931, which is the value of ln 2. And simplification, it gives del S mix equal to 23.05 joule per mole, and it is positive. Okay. Similarly, we can also derive the expressions of the enthalpy of mixing by using the expression of Gibbs free energy of mixing and entropy of mixing. So let us see. We have del G equal to del H minus T del S, or we can say delta G equal to delta H minus T delta S, which is the Gibbs-Helmholtz equation. So from this we can write del G mix equal to del H mix minus T del S mix. This implies del S mix is given by del G mix plus T into del S mix. So now replacing the del G mix and del S mix from equations 6 and 9, we get del S mix equal to RT whole into N1 ln x1 plus N2 ln x2 plus T into minus R into R whole into N1 ln x1 plus N2 ln x2. So this implies del S mix equal to RT whole into N1 ln x1 plus N2 ln x2 minus RT whole into N1 ln x1 plus N2 ln x2. Therefore, del S mix equal to 0, because all the terms in the previous equation will cancel out. Thus the enthalpy of mixing is equal to 0, and it is expected for a system in which there are no interactions between the molecules that forms a gaseous mixture. That means there should be no any chemical reaction between the two gases which are going to be mixed. Again, let us solve another problem. The problem is calculate the entropy of mixing of 1 mole of oxygen gas and 2 moles of hydrogen gas, assuming no chemical interactions occur and the gas mixes ideally. So let us solve this problem. We will use that equation del S mix equal to minus R whole into N1 ln x1 plus N2 ln x2. So here N is a total number of moles, N equal to number of mole of oxygen plus number of mole of hydrogen, which gives N equal to N1 plus N2. This implies N equal to 1 plus 2 equal to 3. Therefore, we can write the mole fraction of oxygen x1 equal to N1 by N, which is equal to 1 by 3, and mole fraction of hydrogen x2 equal to N2 by N, which is equal to 2 by 3. Now replacing N1, X1, N2 and X2 in the equation, we get del S mix equal to minus R whole into 1 into ln 1 by 3 plus 2 into ln 2 by 3. This implies del S mix equal to minus R ln 0.33 plus 2 into ln 0.67, which gives minus R whole into minus 1.1086 plus 2 into minus 0.4005. This implies del S mix equal to minus R whole into minus 1.1086 minus 0.8010. So on simplifying this, we get del S mix equal to minus R into minus 1.9096, which gives del S mix equal to R into 1.9096, and substituting the value of R by 8.314, we get del S mix equal to 15.87 joule per Kelvin inverse per mole inverse. Okay, so the value of del S mix is equal to this. So here is a problem I am giving you as homework. The problem is 1 mole of nitrogen gas is mixed with 3 moles of oxygen gas at 25 degrees centigrade to form a mixture at the final pressure of 1 atmosphere. The initial pressure of each being also 1 atmosphere. Calculate the molar entropy of mixing. This is a very simple problem. I hope you can easily solve it. And if you have any difficult problems you want to solve, and you try to solve it, and if you need my help, then please post the question in the comment box. Together we will solve those type of problems. This is all about for today. Before ending the class, I want to tell all of you that procrastination is a word which means delaying or postponing something. This procrastination actually make easy things harder. If you want to learn something, then do it now. Please don't delay and postpone anything, because we know that time waits for none. We have a limited time period in our life, and we have to do lots of things in this short period. So thank you very much for your patience. If you are benefited by my efforts, please give a like to this lecture, and if you can, please share this video. See you in next class. Till then, enjoy learning. Bye bye.